Integrating radar sensing and communication combines functionalities and resources for cost and power savings. Unlike traditional separate designs, convergent radar sensing and information transmission involves creating combined waveforms and incorporating data into radar signals. Techniques like frequency hopping MIMO radar and phase-attached radar communications aim to enhance data rates without compromising radar capabilities. Challenges involve channel estimation, synchronization, and radar performance decline. Adapted OFDM and IEEE 802.11ad waveforms addresses radar sensing limitations, but trade-offs include reduced data rates for improved velocity estimation. The proposed approach focuses on embedding data into conventional stepped frequency radar waveforms through randomizing parameters to increase data rate with minimal impact on radar performance. It conducts a rigorous theoretical analysis on the effect of phase and frequency modulation on radar sensing functionality, providing insights into radar performance optimization. The main contributions include analyzing the impact of phase modulation on radar performance, proposing a new signaling scheme for data transmission, and efficient implementation methods. The study also addresses challenges in error probability performance and introduces a modified Hungarian algorithm for optimizing the maximum likelihood receiver. Furthermore, it diverse union bounds and nearest neighbor approximations for error probability performance in wireless communication models. In the GSR system model, a transmitter sends a common waveform to both a radar target and a communications receiver. The radar receiver, collocated with the transmitter, processes the reflected signal to estimate target range and velocity. Meanwhile, the communications receiver processes the received signal for data detection. Despite the randomization of the transmitted waveform, the radar operations is analogous to a traditional radar system, with the radar receiver aware of the transmitted waveform. We introduced phase and frequency modulation to embed more data into the radar waveform. By adding frequency modulation on top of phase modulation, we aim to increase data capacity while minimizing impact of radar performance. We analyze the effect on radar sensing using the AF and FIM, and random permutation of frequency tones allows for additional data transmissions with minimal impact on radar accuracy. We focus on the communication performance of the combined modulation scheme, analyzing block error probability with optimal ML detection. Analytical expressions for error bounds are derived, and an efficient communication receiver based on the Hungarian algorithm is proposed. The achievable data rate depends on the total number of waveforms generated. We propose two waveforms for integrating radar sensing and communications: a linear stepped frequency waveform with phase modulations and a frequency permutation-based waveform with phase modulation. We analyze the impact of phase and frequency modulation on radar sensing, finding that phase modulation has negligible effect on radar accuracy. Additionally, we studied the block error probability of the frequency permutation-based waveform for communication, deriving bounds for both AVGN and fading channels. Our findings indicate that frequency permutations result is low side lobe levels, and the phase modulation has little impact on estimation accuracy. Possible future extensions on this work include the quantitative analysis of the effect of phase and frequency modulation on the side lobe structure of the AF. From the communications perspective, it is desirable to extend the analysis to incorporate coding based on which a subset of positive waveforms can be selected to improve the error probability performance. On the other hand, using FCK instead of frequency permutation increases the number of waveforms and allows the use of more DOFs in data transmissions. Nevertheless, the impact of FCK on radar performance requires further analysis.